Hi, I'm Kai Staats, researcher at the University of Arizona, Biosphere 2. It's an honor to be here today to have this opportunity to present to you our work with SIMOC, a high-fidelity simulation of off-world human habitation and bioregenerative life support as a platform for citizen scientists and virtual classrooms. I've had the pleasure of working with Ezio Melotti, lead developer on the SIMOC platform, Tyson Brown from the National Geographic Society, Peter Barnes, Gretchen Hollingsworth, and Michael Pope, who are all classroom instructors who have integrated SIMOC into their virtual and physical curricula over the course of the last year. I will be giving to you a brief introduction to SIMOC, a tour of the interface and how it's used, and then hand it over to Gretchen, to Peter, and to Michael and Tyson as they share their experience of using SIMOC in their respective environments.
We've taken 40 years of NASA data with guidance and input from Paragon Space Development Corporation, the University of Arizona, and Arizona State University to bring to you a high-fidelity simulation and interactive web interface. So you are in charge of building your habitat, choosing the number of astronauts, the duration of the stay, the number of solar panels, batteries, your greenhouse, the plants you want to bring, and you set that simulation in motion to see how well you've done. And in the iterative process of science discovery, you'll be changing those variables one at a time until you achieve the balance that you require for the duration of your mission. Welcome to SIMOC. So we're going to go ahead and proceed. Now here you can sign in as a temporary guest, or you can sign in as an account. I'll sign into my account. Now here's where you would load simulation data, but if you've already downloaded data from a previous run, you want to return to it or share it with a friend. Here we're going to go to new configuration. So we're going to go ahead and run the one human preset. We've chosen a 10-day mission duration, a small crew quarters, one inhabitant, 100 kilograms of food, which is plenty of food for a 10-day mission. We actually only need just 15 kilograms. We have one life support system, no greenhouse, no plants. We have just enough solar panels to get us by and a relatively decent sized battery. Now, if you click on any one of these, for instance, it brings up a small internal wiki on the right-hand side, and this gives you a lot more information about each one of these topics. Now, the graphs. We'll come back to this again when we have a greenhouse, but as you can see, we are producing more power than we are consuming. Now, we could have done all the calculations for you and just made it work, but that's not much fun. So you do have to choose how many solar panels you want. So you can see that if I reduce this to just 20 solar panels, I will not have enough electricity. If I increase it to 100, I have far more electricity than I need. We try to get it pretty close and a little bit beyond. And we go ahead and launch our simulation. And here we go. So the simulation has started. You can see that we have 6 default panels, and this particular panel mission status tells us where we are. How many hours are we into our mission, which also is calculated as Mars days and Earth days, inhabitants, etc. We can also go to this and we can change the panel to, for instance, the mission configuration, which tells you a summary of the original parameters you chose in the configuration wizard. We can also go to, this is my favorite one, the consumption breakdown. And this shows you all the electric devices that consume energy. And if you watch these popping in and out, you'll see that they correlate to what's happening on the right-hand side of the screen. If I back up here, you'll see that when that red line is there, what's on here? The CO2 removal SOUD. CO2 removal is part of the ECLSS rack, and that is currently removing CO2 because we went over the tolerable 0.1%. So as we move through this simulation, you will find that it's relatively consistent. Nothing really changes from start to finish. Why? Because we don't have any plants growing, we don't have any outside influence. It's really the same thing day to day to day throughout the entire 10 days of the simulation. Over here you can look at the oxygen, carbon dioxide, nitrogen, methane, and other variables. And here we have potable water, urine, waste, and treated water. You can see the water vapor is increasing and then decreasing, increasing, and then decreasing, and that's our dehumidifier, which is taking water vapor and converting it back into potable water again. So there's a lot to pay attention to here. Now we're going to stop this simulation, and instead we're going to create a new simulation, and let's go to one human and one radish. Now we've added a greenhouse, a small greenhouse, and we've added radishes. When we come to the graphs, you'll see that there's now information here. We have all this room available, and we're just using this much with the radishes, and we're going to launch this simulation. This time I'm going to change the emission status to the greenhouse plant growth. And this gives you the percentage of growth of the given plant that we have. If we had more plants, more would show. So because the simulation's already done, I'm going to pause it, and I can just fast forward. Watch the plant growth here. Watch this. It's very interesting. And as it moves along, as the plant gets more and more mature, look what happens to these peaks. Remember, these are the CO2 being consumed and the power being drawn for the sake of using the CO2 scrubber in the ECLSS rack. So as we move along, those peaks get less and less, more narrow and further apart until we don't need the ECLSS rack anymore. If we switch back over to the power consumption and breakdown, you'll find that these CO2 modules are not being used. Why? Because the plants are doing it for us. The 40 square meters of radishes is just enough to take the carbon dioxide out of the atmosphere such that these machines no longer have to turn on in order to do it for us. That's the whole point of SIMOC. So what just happened? Huge drop right there, right? So CO2 consumption is down. Okay, let's find out what happened. So let's go back to the greenhouse plant growth. Now watch that, it's at 0. Okay, so something must have happened. So we went from 100 to 0. I'm gonna go one step at a time. One step, and it drops. Now let's go over here and look at biomass. So the biomass was at 11 kilograms and it drops to 5.5 kilograms. At the same time, our food was at 62 kilograms and it goes up to 67 kilograms. So that tells us that something happened. This means the radishes were harvested. Now it takes a few more turns for them to actually be removed from the greenhouse, and you can see they're now at 0% and they're starting over again. So now the radishes are going to grow all over again. They were harvested and the ECLSS rack is activated again because there are no longer any radishes to take in the CO2 and produce oxygen. We are once again reliant on the machines to do so for us. If you're interested in learning more about all of the agents and how they interact, we encourage you to go back to the website and go to the advanced user page.
Hi everybody, my name is Gretchen Hollingsworth and I'm a teacher at the Barrow Arts and Sciences Academy, which is in Winder, Georgia in the United States. When I was given the opportunity to beta test SIMOC, the world shortly after went into lockdown. And so I was quarantined away from my students and we were doing virtual learning. I decided to move forward though and adapted the curriculum materials, which are great by the way. I adapted those great materials and basically designed a week-long independent study for my students to do at home. Basically, the students were able to research Mars and the conditions there and what would be necessary to sustain life as we know it on Mars. They then designed their own Mars habitat, went into SIMOC, tested out the parameters of their design and their different circumstances. They were then able to analyze their data, draw conclusions, and they did a reflection on Flipgrid. So this school year, I decided to use SIMOC as a way to generate excitement around Perseverance landing. A few days before Perseverance was set to land, we did a little bit of learning about Perseverance. We learned about life on Mars and, how far away we are from it or what it would take to be able to get to that point. And we had some really rich, deep discussions. And then I just set them loose on SIMOC for a class and they had a great time. It was so awesome to see them in person because the excitement on their faces and the frustration when their simulations were not successful, priceless is all I can say. Definitely a different experience than our virtual one the prior year. So anyway, whether it's virtual learning or in-person learning, there's so many ways to use SIMOC in the classroom. I appreciate the opportunity to speak with you all today, and I hope you have a great rest of the conference. Thank you so much.
Hi, my name is Pete Barnes, and I teach 5th grade science in New Albany, Ohio. I use the CMOC program with my students this year as part of a about 3 to 4 week study of Mars. We studied all the various aspects of surviving on Mars, and of course followed the lander as it was getting ready to land on Mars, so that was a nice tie-in. And we usually cover a lot of the same variables covered in the CMOC program, including oxygen production, creating food, producing energy, and surviving various hazards on Mars. And then I have my students design a colony, which they eventually put onto Minecraft EDU in a 3D version. So I found the CMOC simulation a really nice tie-in for that, so students could really see how that data all comes together, how their decisions affect their survival, and also how data can change over time depending on the decisions that we make. So I would recommend CMOC, and I hope that the program will continue to develop. Thanks very much.
Ohayo gozaimasu, or good morning from Japan. I am Michael Anthony Pope. I'm a science teacher at Zama American Middle High School, part of Dodea in the Pac East region in Japan. CMOC was a great way to introduce my students to how a real scientist would gather data and use that data to connect and to further research and discovery. With the Mars landing as an additional buy-in, I had students to organize and design a colony and put the variables in place to determine potential outcomes and look for and discuss variables that could be modified and adjusted for further testing. CMOC gave my students the chance to go from what I would call a science observer to a science doer, all in a simple online platform. The CMOC program was an excellent way for me to connect students to the real world of science.
Hi, my name is Tyson Brown, and I am the editorial director for the National Geographic Society's Resource Library. I'm joining Kai and the educator team today to share some background about the education content strategy at National Geographic and how CMOC supports our goals. At National Geographic Education, we believe that young people and the educators who reach them are key to addressing the planet's most pressing problems. We are building game-changing resources powered by our explorers to inspire the explorer in everyone and equip 2.5 million educators with the tools they will need to build empathy for the Earth among 100 million young people. Through this, we will empower 5 million young people to take action and leadership and set them on a path toward becoming the next generation of changemakers and planetary stewards. National Geographic provides equitable, innovative, free geo-learning resources and tools to teachers, schools, and children throughout the world, featuring a combination of geography, social studies, and sciences. The resource library is at the center of this strategy. It is a collection of about 5,000 assets ranging from articles to maps. Users access the free resources in the library from this screen, searching by topic, grade, and content type. An interactive simulation like CMOC is a perfect way to engage students in inquiry and challenge and build their understanding of scientific concepts. Though CMOC replicates a Mars mission, the lessons it offers about the delicate balance that astronauts will have to maintain to survive enables students to think about Spaceship Earth and how its ecosystems respond to human inputs and behaviors. We value partners like Kai and his team at Over the Sun because they are delivering an authentic experience built on deeply researched data and delivered in a delightful manner that attracts students back to try it again and again. As you've heard, educators are utilizing different approaches to share CMOC with their students. The pandemic challenged them, but CMOC's format and delivery channel enabled them to respond. We think that CMOC is the perfect tool for the times, looking forward to continued exploration of the solar system while developing thinking and knowledge that enables students to tackle the problems of today.
I do hope that you enjoyed the presentation and found it informative and perhaps gave you some ideas for how to integrate SIMOC into your classroom. You can learn more at SIMOC.space. Thank you.